Our next topic on graphs is going to be about search, and in particular, some of the applications of search and a couple of the basic search methods. So the particular ones that we always hear about are going to be the breadth first and the depth first searches. And both of these methods have several applications that we can use for them. And even though we talk about them in very different terms sometimes about which one to use, the difference between them as far as implementation is very, very simple. Basically, the only difference between the implementation of a breadth first and a depth first search is whether you're using a queue or a stack. So for both of these search approaches, the basic idea is that you are going to start out by visiting nodes, and we will pick a node to start with, so whatever the starting node is, and then we will visit, or I shouldn't say visit, we will look at its neighbors. And then if they are unvisited, then we'll do two things. We will mark them and add them to either a queue or a stack. Okay. And so the queue is going to be for a breadth first search, and the stack is going to be for a depth first search. And then you will pull the next thing, the next node, off the queue or the stack. And you keep doing this over and over until you run out of stuff on the stack. And so what that's going to do is it's going to visit all of the elements of the tree, all of the elements of the graph in order. If it is a breadth first search, it's going to start from a single node and it's going to sort of spread out from there. You can think of something like spilling water out and it just spreads out to all the adjacent ones. If you're doing a depth first search, it's like you can imagine you're going to just run as far as you can until you can't go any farther, and then you back up and you keep running down paths, kind of working your way backward. If you remember when we talked about backtracking as a method of doing a brute force search of state spaces, well, if you think of a state diagram as a graph, then the depth first search is sort of like a way that we do backtracking for exploring a state space. Okay, but if that didn't make sense to you, don't worry about it at the moment. Now, each of these search methods has some nice features of its own, some nice ways that it can be used. So for the breadth first search, if we have an unweighted graph, then this is going to give us a shortest path algorithm. So basically, the breadth first search will tell us how many steps we have to take to get from a starting node to some other node. Sort of the breadth of the graph is going to be obtained there. So you get that information from the breadth first search. The depth first search is sort of the basis for a lot of other algorithms, and it's a very nice stepping stone. And one of the things we can do with the depth first search is it allows us to do things like ordering a tree. So just keep in mind that DFS we can use as the basis for other algorithms, and we will see some of these later on. And in particular, this is going to let us find, I'll say, descendants and ancestors and look them up much more easily. So I'll illustrate a little bit of that in just a minute. And both of these search techniques, there's a lot of sort of basic problems that you can use that are based on each of them. Okay, so let me illustrate. It's usually the easiest way to illustrate this is to actually show a graph and kind of the elements of a graph and what it would look like to run all of these various techniques on each one. Okay, so here's a graph. I'm going to label the graph with numbers that just to indicate the nodes so that I can talk about each one. Okay, so there's 8 nodes in this graph. And I'm going to just assume that I'm starting at node 1 for a minute. So if I want to run a BFS, so if I'm going to run a BFS, I'm going to keep track of a queue. So there's going to be a queue of elements that I have here, and I can keep track of the distance that everything is away if I would like to. So I can start off by making the distance of everything that I see along the way as infinitely far away. You can set it to -1 or something like that if you want to, but you can say that something's infinitely far. There's just some value that you use to mark that you've never seen that node before. And you start with your starting node and you say it's got a distance of 0. Okay, and what you do is in the queue, you start with the thing that you have and you mark it and put it into the queue. So right now, 1 is the only thing in my queue. And then what I will repeatedly do is I will take a node off of the queue. So I take number 1 off. So I'm looking at number 1 right now, and I look at everything that it's adjacent to, and I make them a distance 1 farther than I am. So since I'm currently at a node that's a distance 0, I would look at node 2, and I would say it's a distance 1, and I would put it on the queue. I would take 3 and make it a distance 1 and put it on the queue. And I would take 7 and make it a distance 1 and put it on the queue. Okay, so I've now enqueued those 3 elements. And now I'm done with node 1. Well, now I pull the next thing off of the queue. That's number 2. So for 2, I look and I see what are the nodes that are adjacent. Well, it's adjacent to 1, but I've already seen that. It's already got a value. And I've got 4 over here that's adjacent. So I would mark 4. Notice that 2 has a distance of 1. So 4 is now going to have a distance 1 more than that. So it will have the value 2. And I go ahead and I enqueue 4. Then I pull the next thing off of the queue. That would be the number 3. So I look over here at 3, and I'm done with 2 now. I look over here at 3, and I see what it's adjacent to. Well, it's adjacent to 1, but that already has a value of 1. It's adjacent to 5. That one's at infinity, and so I set 5 to 1 more than what 3 is, so that will have the value 2. And I enqueue 5. Okay, now I'm done with node 3. The next node is node 7. So 7 is over here. It's at a distance 1 away. I see what it's near. Well, it's near number 1 and adjacent to 1, but that one's already got a value of 0. It's adjacent to 2 or to 5. That already has a distance of 2. So I'm done with number 7. I don't need to look at it anymore. The next one that I pull off is going to be node 4. So I go back here to node 4, see what node 4 is adjacent to. It's adjacent to 2 that already has a value, and it's adjacent to 6. So 6 gets 1 more than wherever I am now, which is 3, and it will get enqueued. And I'm done with node 4. The next one I pull out is node 5. So node 5 has a distance of 2, and it is adjacent to 3, which already has a value, 7, which already has a value, and 8 does not have a value. So I increase that by 1, which is 3, and I enqueue 8. And then finally, I pull off 6. 6, everything it's adjacent to is already set, and likewise 8, everything it has is set. So you'll notice that we have the distance, how far everything is away from our starting node. So the starting node itself is a distance 0. Nodes 2, 3, and 7 are a distance 1. So you can see they are there. Nodes 4 and 5 are a distance 2 away, and 6 and 8 are a distance 3 away. So we can sort of see how the breadth, how this spreads out from the original starting point. Okay, so I'm going to try to undo all of these and go back to my original one, and I will show you how this same graph would work if I was doing a depth first search on the same graph. And I'll give you an example of how it might work. Okay, so now if I'm doing a depth first search, instead of having Q, I'm going to have a stack. Okay, and so the stack is going to keep track of what nodes there are along the way. And the nice thing about a depth first search, and one of the ways that we will tend to use it, is we will keep track of the depth that we encounter along the way. So as we do a DFS, we'll sort of keep track of the time that we first encounter a node and a time that we are done with the node. And so I'm going to mark that on each one. I'm going to mark the point we start and the point we end. Now, a DFS does not give us a shortest path the way that the BFS did. Okay, and again, it's because it's an unweighted graph. But DFS does not give us the shortest path on an unweighted graph, but it will work for some of these other algorithms. So I first am going to start here at node 1, and I'm going to have a starting time of 1, and I'll mark that. Actually, I'll mark that in green. Why not? So the starting time is 1 here. And I will say, I will look at all of its adjacent nodes and I will put them onto the stack itself. So 1 has nodes 2 and 3 and 7. So I can put them onto the stack. I will put 2 and 3 and 7 onto a stack. And I'm not done until all of those things are finished processing. So the next thing I will do is I'll basically make a recursive call down to the next thing on the stack. So I'll pull the 7 off, and I'll go over here to node 7. So I hit that at time 2. Okay, and so for node 7, I look at everything that it has. Well, number 1, it already has a starting time set. It already has the 1 set, so I can't go there. And so I will put the next thing I see, which is a 5 on the stack. Okay, so I'm not done with 7 yet, but I look at the next thing on the stack. Well, that's node 5. So I'm going to get here. This will begin. I'll reach it at time 3. And then I'll look and see what I see from there. Well, I see node 8 down here, put it on the stack, and I see node 3, and so I'll put it on the stack. So I pull the next thing off. In this case, it's the node number 3. So now I've got time 4 is when I hit that node, and I look and see what it's adjacent to. Well, it's adjacent to 1 that's already been started, and it's adjacent to 5, which has already been started. So now I'm going to finish with node 3 at time 5. So I got there at time 4 and I finished at time 5, and now I'm all done. Okay, I come back here to number 5 and I look and see what it's adjacent, or I look at the next thing on the list, which is number 8. So if I pull 8 off of my stack, then it's going to now have time 6 is when I hit number 8. And I'm just going to run through this rather than work through every little detail of it. So you can see that you'll hit this at time 7, and you'll hit this at time 8, and then you will hit this at time 9. And notice one thing that happens along the way here is eventually I would end up and I would have 2 on the stack multiple times. And so when I pull it off later and get to the very, very bottom of the stack, I would have already encountered it. And so finally I finished this at time 10, and this at time 11, and this at time 12, this at time 13, and this at time 14, and this at time 15, and this at time 16. And so if you imagine then that this entire thing has formed a tree sort of showing the direction that everything traveled, we get this DFS tree along the way here that shows you kind of the depth that's there. And so notice it's a very different path from what we had with the BFS. So we went from 1 to 7 to 5 to 8 to 6 to 4 to 2. That's sort of all one path, even though we could have just gone straight from 1 to 2. But that's not the route we follow. We follow this more convoluted route because we're trying to go as deep as we can. We sort of keep pushing forward farther each time. Okay, so again, the DFS is useful. The reason why you might want these starting and ending times is they give you a bound over everything that's a child of that node in this graph along that blue tree. So for instance, 1 to 16, well, that's going to be everything. Every node has values between 1 and 16. But if there's a node and you look at it and you say, well, is 6 a descendant of node 1? Well, sure enough, 7 to 12 falls inside of 1 to 16. Therefore, it is a descendant of it. And likewise, if I compared it to 6 and 5, I would say, well, yes, 7, 12 falls in between 3 and 14. Sort of this range falls in between that range, and therefore 6 is a descendant of 5 in the depth first search. And we're going to use that sort of idea later on in some future algorithms. Okay, so I want to talk now for a minute about some of the applications that we can have for a depth first search or breadth first search approach to problems. So one of the applications that we have is if we just want to find connected components, we want to see which parts of a graph are connected to other graphs or other parts of the graph, and we actually just want to loop through. Well, to do this, you can run either BFS or DFS and mark every node visited. Okay, and every node visited is they are all part of the connected component. Okay, now later on, we're going to talk about something called a strongly connected component in a directed graph. We're not going to do that right now, but later on, we'll come back to strongly connected components, and that has a slightly different meaning. But this was just basically says, are things connected? Now, another thing that you can do along the way besides that is you can use a union find data structure to group things together. So once you identify that they're connected, you can use union find to group nodes. So you don't actually have to necessarily run the BFS or DFS, but you can basically, as you run it every time you encounter a node, you get a result there. Okay, another thing that you can do is what is called a flood fill. And this is a technique that it's exactly what is used in computer graphics. If you're using something like Photoshop and you're matching a color, or you're filling in color, or filling in regions, there's a few variations on flood fill, exactly how it works. But the basic idea of flood fill is that you are going to do a search over a grid. So your original thing is a grid, and typically what a flood fill says is I've got some color in here. For instance, every cell in this grid might have some value. And so I'm going to just mark these with black. If they have the value for black, and maybe there's other things that have the values for red, and here's one that has the values for blue. And maybe there's another region that is green. Okay, so if I have a graph like that, what a flood fill will do is it will let you say, okay, I want to turn all of the green things red. And so you would select one green thing, and then you would basically do this search over all things as long as it's connected to other green things and change those values to red. So that's the idea of a flood fill. And so so what you do in order to do this is you basically do a BFS or a DFS. To find adjacent cells, and if the same color, you change to the new color. Okay, so in that earlier example, or let's say this one right now, say the blue example, say I wanted to turn everything in this graph currently that's blue to green, I would start out with something that I knew was blue here, and I would do, let's say I do a depth first search. I would go from there to here, and guess what? That's blue, so I change it. I go there, it's not blue. I go down here, it is blue, I change it. I check there, not blue. Check here, it is blue, not blue, not blue. I work my way back up. I check this. It is blue. Look down. No. yes, no, yes, no, yes, yes, no, 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 yes, no. Okay, so I would end up checking basically every edge, and as long as I kept finding stuff that was blue, I would go on from there. And if I ever got to a cell that was not blue, I would stop and just go back. Okay, so that's an example of how you would use a depth first search, and it would work the exact same way with a breadth first search. It's very simple. It's actually a very simple piece of code to write to do what's called flood fill. So another example that we can have is we can have what's called a bipartite graph check. So we can see whether a graph is bipartite, and what bipartite means is you can divide. We can divide this into two groups with no edges within either group. So the only edges, what this means is there are only edges between them. Bipartite graphs come up all the time in all sorts of applications, or there's times that you want things to be bipartite. And what that means is you can have edges, but basically every edge has to cross this boundary. So you can imagine that there's like a boundary, and so I have the stuff on one side and I have the stuff on the other side, and all of the edges cross that boundary. There's not going to be any edges like the green one that you see there. That's not allowed in a bipartite graph. And so sometimes you're given a graph and you want to say, is it bipartite? You don't know ahead of time. Well, it's actually very easy to do that by doing either a breadth first or depth first search. The idea is you label the starting node in group one, and then each step you label with the opposite group. And then if you ever have two of the same group adjacent, then it is not bipartite. Okay, and the nice thing about this is you're not just determining is it bipartite, but if it is bipartite, you've actually labeled everything as one or two. So imagine that I just have some graph, something like this, and I want to know, is this a bipartite graph or not? In other words, is there a way to label it? Well, I would go through and I would label the first thing 1, and then everything it's adjacent to would get labeled 2. Okay, and then anytime I go to a 2, anything adjacent to it, I need to label a 1. And so that one worked. If I go down to this 2 down at the bottom, the 2 things next to it are both labeled 1. If I come back over here to this 1 over here, I look at everything next to it, it's labeled 2, everything works. Okay, I apologize. I had a bit of a computer hiccup there. But the idea is if we have something that is not a bipartite graph, like let's just say that we have something with 5 nodes in a cycle, there's no way that you can label them where everything can be labeled with a 1 and 2 without 2 of the same number coming up together. So we might label this first thing with a 1, and then its adjacent ones get 2. And then for one of those, its adjacent one would be 1. We'd go over to that 1 and it would get an adjacent value of 2. And now you get 2 things that are the same next to each other. And so it is not a bipartite graph. So one of the nice things about this method is this not only tells you if you have a bipartite graph or not, but it also actually gives you a labeling that works if it is possible to have one. Okay, so our next application, it's one that comes up a lot in a variety of sort of real-world applications is what's called topological sort. And the idea of topological sort is you want to sort a variety of tasks or things that have to be done before other things. And you need an ordering, you need a sorting of the various tasks so that the things that have to be done before other things are done first in the ordering. And so, a common example that people use is, well, if you put on your socks before you put on your shoes. So socks have to come before shoes in a topological sort. So more generally, the way a topological sort works is we have a series of tasks, and they might look in different ways that there's some priority, and typically there's a directed edge saying you have to do item 1 before you do item 2. And this can get kind of arbitrarily complicated. I'll just draw one here as an example. So there's a possible example, and I'll label these nodes just so I can refer to them with some numbers here. Okay, and we can actually use a variation of a breadth first search or a depth first search to do this. So let me show you the depth first search. So if you want to use a DFS to find a topological sort, you're always, both DFS and BFS, you will always start from a node with n degree 0. And then you run DFS. And when you finish with the node, you will put it on a stack. And so let me show you what I mean by that. So we might take some path through here, and I'm going to draw another edge in here just to make it a more interesting path. But I go ahead and I do some depth first search through here. So maybe I take that, and now I'm done. I can't get any farther, right? I went from 1 to 3 to 6 to 7, and I'm stuck. I can't go any farther than 7. So I go ahead and I put 7 on the stack. Okay, then I go back to 6. Well, 6, I can't do anything else with 6, so I'm done with 6. And so I put it on the stack. I go back to 3. Well, 3, I can go forward to 5. And then once I'm at 5, well, I've already visited 7, so there's nothing else I can do there. So I put 5 on the stack. And then I go back here to 3, and there's nowhere else I can go from 3. So 3 goes on the stack. And finally, I go back to 1, and there's nothing else I can do with 1. So 1 goes on the stack. Okay, I haven't hit every node yet, but I have sort of finished those out. So now I start with 2, and I go from 2, and I do a depth first search down to 4, and 4, well, it can't go to 5, it can't go to 6 because those are done. So now 4 is done, so it goes on the stack. And then back to 2, well, now both 3 and 4 have been finished, so I'm done with 2, and I put it on the stack. And finally, I read off the stack in order. So I get 2, 4, 1, 3, 5, 6, 7. And if you look at the topological graph here, you'll see if you do things in that order, you're never doing something before the things that come before it have been done. So if I do 2, and then I do 4, well, notice the only thing 4 needed was to have 2 done. Then I do 1, that's fine. I do 3, well, notice both 1 and 2 have already been handled, so it's okay to do 3. When I get to 5, which is the next thing, well, guess what? Both 3 and 4 that needed to come before 5 have been done. And likewise for 6, both 3 and 4 have been done. And when I get to 7, both 5 and 6 have been done. Okay, so that's an example of how you can use a depth first search to perform a topological sort. It's basically a standard depth first search. And the only difference is that when you're done with a node, you go ahead and you stick it on a stack at the very end. Okay, so the other variation is something that is a whole lot like, although it might not look like it right at first, it's a whole lot like a breadth first search. I'll just erase all of this for a second, and we'll see how this works. So the idea of using a breadth first search is that we will take all the nodes within degree 0. And basically, you put them into your queue. Okay, so we'll put them into the queue, and then you will remove them from the queue, just like we do with the normal breadth first search. And then every time you remove one from the queue, you remove the edges coming from it. And if that makes something else have in degree 1, or in degree 0, I mean, then we will enqueue that node. Okay, so in this case, we might start out and we look at our graph here and we say, okay, so here's going to be my queue, and I'm going to have 1, and I'm going to have 2 in the queue. Okay, so my overall ordering, I'm going to have 1. Every time I pull something out of the queue, that'll be it. So I'll pull 1 out of the queue. And when I do that, I say, okay, I've marked 1 as the first thing, and I remove every edge that's there. So I'll remove that edge. Okay, well, 3 still has an in degree of 1. Nothing happens yet. So then I pull the next thing off of the queue. That's the 2. So I mark that down here, and I remove all of the edges coming out of 2. Well, notice that when I do that, now 2 new nodes have in degree 0. Both 3 and 4 have in degree 0. So I put them into the queue. Then I pull the next thing out, and just to illustrate what it is, they don't have to be in that order. 4 and 3 are both in degree 0. So if the next thing I pull off is 4, I pull that off and I get rid of those edges. We'll notice that at this point now, 6 has in degree of 0. Okay, now I pull the next thing off. That's the 3. I remove all the edges from the 3, and now 5 has in degree of 0. The next thing I pull off is 6. When I do that and remove its edge, 7 still has an in degree of 1, so that doesn't help me. I pull off 5, remove its edge, and notice now 7 has an in degree of 0. So I put it in the queue, and finally I pull that out of the queue, and that's the last one. And so notice now, if I were to do things in the order 1, 2, 4, 3, 6, 5, 7, again, that works just fine. That's a perfectly valid ordering. It's a different one than we got before, but it's still a good topological sort. Okay, so topological sort, you can either use your breadth first search approach or your depth first search to achieve that. Now, there's one final thing that I wanted to mention, and it's not particularly an algorithm of its own, but it's something that's very useful in other algorithms, and that is identifying what's called a back edge. And the way to do this is in a DFS. This is an edge to a previous node, and in particular, a previous node that you've started exploring, one that you started but haven't finished. Okay, so if I were just to draw a diagram here of, maybe let's get rid of that, of maybe a complicated, it's not even very complicated, but some graph like that. And I were to start over here at node number 1. Let me label all these nodes. Okay, and I start doing a depth first search, and so I go from 1 to 2. And if you remember, I might mark the time that I encounter each one, 3, 4, and I happen to have nicely labeled them in the same order that I encounter them. And I go here to 5. Well, now 5, when I get here to node 5, notice there's 2 edges here, and both of these go to things that I've started exploring from, but I haven't finished. And those are called back edges. because they go from the current node that I'm on and they connect up to a node that I've started on already. So they're edges that I don't want to follow, that I don't want to visit. And so what a back edge implies is this is going to imply that there is going to be a cycle. And in particular, if you look at that kind of blue line, if I were to connect that blue line up with either of the two back edges, I would get a cycle in the graph. And so this is a way of identifying where a cycle might be, or if a cycle exists in a particular graph. If you have a tree, trees don't have cycles. If you have a tree, you're not going to have any back edges. So that's one of the nice ways of identifying if your graph is a tree and you don't know it ahead of time. Back edges have some other uses also, but that's kind of the main one. They're sort of the most basic one, is identifying if there's a cycle or not. Okay, so we've seen the breadth first search and the depth first search, and we've seen a lot of applications of both of them. You're going to get a chance to try these out on the problems in the class. So hopefully this was a good review / introduction, depending on exactly what your background is to these.